Okay, so this is an example from chapter 6, and the main takeaway of this is that if we have a B field, essentially, and we're moving a conductor through a B field with a velocity, we can induce a current in a conducting circuit by moving the conductor through the B field. So in this case, we have a metal bar that's sliding over a pair of conducting rails. So because it's touching these rails, it's essentially completing a circuit. Okay? So it's sliding through a uniform magnetic field B, and so this dot basically means that the B field is coming out of the page. So a good way to remember it is kind of like if you think about an arrow, like the tip, if it's like the tip of the arrow coming out, really. Okay, so it's this bar is moving with this constant velocity, which is u, written as u in the problem, and we're trying to determine the open circuit voltage V0 that appears across the terminals 1 and 2. Okay. So if we want to find, if we find the voltage here, it'll be equal to our open circuit voltage over here. So these two will essentially be equal. Okay, so the way that we're going to do that is we're going to use this general equation here, and we know that our velocity crossed with B, dotted with DL, integrated from these 2 points, is going to give us our open circuit voltage. Okay, so in this case, we're just looking at our directions, right? So we have our velocity is going this way. So velocity is in the x hat direction. So we're just plugging in V0, just like a constant initial velocity in the x hat direction. And then we have our B0 is in the z hat direction because this is x and this is y, and our B is coming out of the page. So it's going to be in the z hat. Then we're dotting it with this DL. So the differential line across our bar, our conducting bar, and our DL is the direction that we're modeling our current in for the circuit. So our DL is in the y hat direction. Okay, so now we have x hat, right, cross z hat. So our x hat crossed with z hat, and then we end up with negative y hat. So if you remember the right hand rule, so it would be like your pinky, your hands upside down, along x, swept to z will give you negative y. Okay, so we just have our constants out here, multiplied by each other, and then negative y for our solution here. Okay, so negative y dot dl in the y hat. So we know that y hat dot y hat is equal to 1. If you dot a directional unit vector with itself, it's equal to 1. And then we can simplify this equation even further, and then we have v0 multiplied by b0 and times the integral of dl. So in this case, we could do this as like z or anything, but this is just like a static height from 1 to 2. And the problem in this case just had it as h, so the height from 1 to 2. But you could write this as y or whatever else you would like to from this. So just the distance from 1 to 2. So this is the final solution for how to find the open circuit voltage here. Next, we're going to look at the Faraday disk generator, which is a little bit more complicated. So we're adding a few more things onto this.